In this screencast we will look to cover a concept of chemical bonding known as hybridization. We will first briefly look at what hybridization applies to and why it happens. Next, with the help of an analogy we will understand how hybridization happens in a carbon atom. Now, what is hybridization? We know for a fact that a simple covalent molecule will possess a specific shape. This depends on the number of electron pairs around the molecule's central atom, and these pairs are held in either atomic orbitals or covalent bonds. Now, we also know the usual shapes of atomic orbitals and covalent bonds, however we observe that the actual shapes of simple covalent molecules do not tally with the orbitals being used. We therefore theorize that the atomic orbitals of atoms can somehow mix to give four identical orbitals which will have hybrid character, both s and p, that can result in the actual observed shapes in molecules. This mixing of atomic orbitals is what we call hybridization. Hybridization is frequently discussed using carbon molecules as an example. It is well known that carbon forms four bonds, however depending on the types of bonds formed around a carbon atom the shape changes. But before we look at exactly how carbon undergoes hybridization, we will first go through a related analogy. Let's say that I have four friends over for a house visit. I want to serve them some refreshments, so I look in my fridge and find some fruit juice. I have exactly 4 glasses left, 3 glasses papaya and a glass of strawberry. Now, I decide to be fair and mix all my fruit juice together, creating a unique fruit punch. I then serve my friends this fruit punch, exactly 1 glass for each friend. They comment on the unique taste and ask, "Wow, what's this juice? It tastes of mostly papaya with just a slight hint of strawberry flavor." I proudly tell them that they are drinking my very own straw papaya cocktail. Now let's reset the scenario. Again I have 4 friends over at my place, but this time one of them has a serious allergy to strawberries. I have the same amount of the same juices, but how do I serve them now? Because of the allergy I'll have no choice but to reserve a glass of pure papaya for my allergic friend. I then again be fair to the rest and mix my remaining juices, 2 glasses papaya and a glass strawberry, to create another unique fruit punch. I then serve, my allergic friend gets the papaya and the other 3 get to taste my new fruit punch, again a glass each exactly. They tell me they taste both papaya and strawberry, but more of papaya. So I decide to coin this cocktail of mine strawpaya. So, what if now 2 of my 4 friends were allergic to strawberry? If we can follow the pattern, we'd realize that now I need to reserve 2 glasses papaya instead, creating another unique fruit punch that I'd now call strawpa. And we can also probably guess that this new cocktail tastes equally strongly of both strawberry and papaya. So how does hybridization really take place in simple covalent molecules? When a carbon atom is to form 4 covalent bonds in a molecule, it needs all its 4 orbitals, 1 2s and 3 2p, to be singly filled. Therefore simple excitation first occurs just to promote 1 electron to fill the previously vacant 2p orbital. Now let's consider the methane molecule first. In methane C forms 4 CH sigma bonds of equal length and equal angles apart. For this to happen all 4 CH bonds must be formed by head-on overlaps by identical orbitals. Therefore it must hold true that the original 4 atomic orbitals of the C atom must first mix, producing 4 identical hybrid orbitals. This mixing process is what we call hybridization. Once the hybrid orbitals are formed, bond forming occurs and the molecule acquires its observed tetrahedral shape. The central C atom of methane is now labeled as being sp3 hybridized and we name the hybrid orbitals sp3 orbitals. Now, what about the ethene molecule? In ethene, the 4 bonds that C form are no longer all identical. 3 sigma bonds are of equal angles apart and 1 pi bond is formed between the 2 C atoms. It should be noted that pi bonds can only be formed from p orbitals, so 1 2p orbital of each C is reserved for forming the pi bond while the 3 remaining orbitals of each C undergo hybridization, yielding back 3 identical hybrid orbitals leading to the 3 sigma bonds formed and the observed trigonal planar shape. We now label the central C atoms of ethene as sp2 hybridized and the hybrid orbitals sp2 orbitals. Finally, we quickly consider ethine. Ethine has 2 sigma and 2 pi bonds, so each C atom reserves 2 2p orbitals each for forming the 2 pi bonds, while having the remaining 2s and 2p orbitals undergoing hybridization. The end result is a simple linear shape for ethine, its C atoms being sp hybridized and its sigma bonding orbitals being sp orbitals. Now, we draw important links of C hybridization with our fruit juice analogy earlier and consolidate a few important points as conclusion. Mixing 4 different glasses of juice gives back exactly 4 glasses of fruit punch. In each hybridization scenario, the number of atomic orbitals mixed always produce the same number of identical hybrid orbitals in return. I name my fruit punches differently depending on the ratio of juice mixed. The higher the ratio of papaya in the fruit punch, the more its name reflects that. Just like how we label the central atoms of the molecules, sp3, sp2 or sp, which simply depends on the number and what type of orbitals are mixed. Essentially, the name says it all. The taste of each fruit punch is different. When we do a direct comparison of CH bond lengths between methane, ethene and ethine, we see a clear trend: the bond lengths decrease. This makes sense once we recall that for the same shell, s orbitals are closer to the nucleus than p orbitals. Therefore, in a sp3 hybridized atom, its sp3 hybrid orbital would be longer than the sp2 hybrid orbital in a sp2 hybridized atom, due to the greater p character in the former. Likewise is understood for comparison of sp2 to sp hybridization.